Pluto is a far-off and confounding planet that was once essential to our nearby planetary system's family. However, upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a startling disclosure. They suggest that it is on a possible trajectory to collide with Neptune. Yet how could this occur, and what might be the aftereffects of such a huge event? Are we seeing a looming crash, or is there something else about this approaching colossal mishap? Join us as we investigate the possible results of a Pluto-Neptune impact. Pluto, a former planet that was renamed a dwarf planet partly due to its remarkable orbit, remains a subject of interest and study in the scientific community. As shown by recent estimates by leading experts, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential dangerous impact between these two planets that could imply a huge liability to Earth. How is such an event even conceivable? Pluto's trip around the Sun is unlike any other planet in our nearby planetary group. It requires a stunning 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its phenomenally twisted shape, deviating drastically from the nearly round orbits of the major planets. What makes Pluto's orbit even more curious is its inclination set at 17 degrees to the ecliptic plane. The way Pluto follows its path is much more extreme compared to other planets. This inclination and anomaly add layers of complexity to its orbital dynamics. Potentially one of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the nearby planetary system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to figure out its odd orbit. Unlike other planets whose orbits lie fairly close to the ecliptic plane, Pluto's path sticks out with its steep inclination and irregular shape. The mystery grew with the realization that Pluto's orbit does indeed cross Neptune's. The complexity of Pluto's orbit amidst these intricacies is proof of the complexities of space mechanics. The three-body problem in space is about figuring out how three objects in space like Pluto, Neptune, and the Sun move and influence one another with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. For Pluto's situation, this problem shows how its orbit, Neptune's path, and the Sun's gravity all work together in a complicated way. The terms alpha libration and degree libration, along with the VZK influence, are key to this riddle. As indicated by astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. Concerning Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is situated around 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from influencing each other. Expansion libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated well above their orbital plane, providing an extra layer of protection from potential collisions. Another significant factor is the VZK influence, named after three scientists, Vysotsky, Zippel, and Klemperer, who studied how objects move in space. It's about how three celestial objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pull affects how they move. In Pluto's case, the VZK influence helps us understand why its orbit around the Sun is so unusual. Despite Pluto's orbit seeming chaotic, this influence helps keep it moving smoothly. The VZK influence shows that although things in space might appear wild and erratic, certain patterns and rules maintain control. These factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or lose its course. Mathematical simulations in the late 1980s revealed that despite these stabilizing factors, Pluto's orbit is still somewhat turbulent, with minor variations in initial conditions leading to massive differences over long periods. However, these surprising properties of Pluto's orbit have been found to maintain stability over exceedingly long timescales, effectively keeping the chaos in check. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a unique relationship with Pluto, where for each orbit Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's orbit stable. However, Neptune isn't alone in this. Jupiter's gravity also plays a significant role in protecting Pluto's orbit, and Saturn contributes as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for a long time, even billions of years. It seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues moving safely through space without running into problems. These phenomena are critical in understanding the universe as they maintain the order and consistency of celestial bodies' movements. Without these forces, the solar system as we know it would be a place of far greater disorder and unpredictability. Bodies like Pluto might crash into others or be ejected from their stable orbits, causing a domino effect on other celestial bodies. For Pluto especially, with discussions about it possibly crashing into Neptune in the future, understanding its orbit is crucial. This gives us a clearer picture of the dynamics of our solar system. The case of Pluto shows how even the most seemingly unstable orbits can achieve a state of stability through the intricate exchange of gravitational forces and orbital mechanics. It also highlights the importance of constant observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect example of this anomaly. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or velocity can dramatically alter its long-term trajectory. In the vastness of our solar system, Pluto occupies a unique position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study leading to significant revelations about its structure and behavior. One of the most captivating aspects of Pluto is its surface, which is a complex tapestry of ice, rock, and various compounds. NASA's New Horizons mission, which flew by Pluto in July 2015, provided remarkable data about this distant world. The surface of Pluto is characterized by vast fields, towering mountains, and deep valleys. One of the most remarkable features is Sputnik Planitia, a giant heart-shaped plain made primarily of nitrogen ice. This area showcases a variety of landforms, including massive ice shelves and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active despite its perfect distance from the Sun and low temperatures. Another fascinating aspect of Pluto is its atmosphere, primarily composed of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere is thin but shows interesting seasonal variations. As Pluto moves closer to the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface. As it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply revolving around Charon. This unique relationship contributes to the complex gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to various other dwarf planets and potential impactors. This belt is a repository of ancient material from the early solar system, giving scientists a glimpse into its formation. Pluto's orbital characteristics may provide insights into the formation patterns of these distant objects, suggesting that interactions with larger planets may have played a critical role in shaping their current orbits. One of the key implications of understanding Pluto's orbital elements is the potential impact on how we understand the solar system's evolution. Gravitational interactions from neighboring giant planets like Jupiter and Neptune can alter the orbits of smaller bodies, including those in the Kuiper Belt. Such interactions can lead to changes in orbits, potentially resulting in collisions or ejections from the solar system. As researchers continue to study the details of these interactions, they may uncover broader patterns that govern the behavior of celestial bodies throughout the universe. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to rename Pluto as a dwarf planet in 2006 was controversial, sparking debates about the nature of planets. In any case, Pluto's orbital relationship with Neptune and its position in the solar system serve as powerful reminders of the complexity of the universe. Through continued investigation, we can deepen our understanding of these distant worlds and the forces that govern their motion. As we continue to explore Pluto's unique orbital elements, it is essential to recognize how the gravitational forces exerted by distant planets shape the behavior of objects in the outer solar system. While Pluto's orbit may appear chaotic at first glance, it is precisely these intricate interactions that allow it to maintain stability despite its apparent instability. By delving deeper into the mechanics of Pluto's orbit, we uncover more layers of complexity, shedding light on the dynamic processes that govern the motion of celestial bodies. One particularly intriguing aspect of Pluto's relationship with Neptune is the long-term stability of their orbits despite their occasional proximity. This stability is due to a special resonance between the two bodies known as a 3:2 orbital resonance. For every 3 orbits Pluto makes around the Sun, Neptune completes 2. This resonance keeps Pluto and Neptune in a stable configuration, preventing them from colliding despite their orbits crossing. The stability provided by this resonance is a rich example of how gravitational interactions can ensure the orderly movement of celestial objects. Each time Pluto and Neptune approach each other in their orbits, their gravitational fields interact in a way that ensures their paths remain synchronized over long periods. The result is a system where even as Pluto crosses into Neptune's orbit, the two bodies are always carefully spaced apart by the steady resonance. Thus, the likelihood of a collision is virtually non-existent.